let me continue the next section. CS 72 is the subject code. Now this is an introduction class. So in the introduction class, we have gone through what is meant by a computer architecture, what is the prerequisite for you to understand this course, and why this course needs to be studied, the path that you need to follow for understanding. Everything was discussed in detail, right? Now if you want this course to be in tune, now let me discuss the course objectives. The course objectives the computer you are going to look into the word computer architecture. Probably in your computer organization subject you would have studied a general computer architecture, but here the same general computer architecture is going to be ported into different architectures, right? Now once when you are familiar with the computer architecture, the next thing you are going to look is measure the performance. Right? The second objective is you are going to measure the performance. Now the question is, why do we need to measure the performance? Because there are different computer architectures available. If different computer architectures are available, somewhere we need to choose the best one suited for a particular application. Now the parameter that is used for choosing is simply performance. Now we are going to look into the various performance metrics. Based on that you are going to make a choice of an architecture. And the third one is you are going to look into a parallel programming. Parallel programming concept is also looked into it, but here we are going to look into the same architecture from a software point of view. From a software point of view, the first two probably looks into the hardware issues. The third objective is going to look into the software issues, right? Now these are the course objectives that you are going to study. Now coming to the prerequisites. Prerequisites are nothing but the things you should know to clearly understand the subject. The first requirement is you should have a knowledge of a basic computer architecture, right? I think you would have studied in your first semester the functional block diagram, and again in your computer organization you would have studied a general architecture, and again with reference to a particular architecture you would have studied in a microprocessor 8086, like that. You have a knowledge of what a computer architecture is all about. And then the next thing that is you need to know about microprocessors and microcontrollers. So these two things are needed to be known. And again a little bit on parallel programming concept, right? Now I think these three prerequisites are already known to you. The first one is understand the basic computer architecture, that you already know about it. You have studied in your first semester as well as in your fourth semester CO subject. The next one is you should have a brief knowledge about microprocessors and microcontrollers. This microprocessor and microcontroller gives you the layout of a particular processor. And then the last one is parallel programming concepts needs to be known to you. And again in your first semester you would have executed few problems on parallel programming, right? Now these are the prerequisites needed for understanding the computer architecture subject. So once when you are clear with the objectives and the prerequisition, let us go to the outcome of the subject. What is meant by outcome? Outcome is nothing but the thing that a student is guaranteed to learn at the end of a course, right? Course outcomes. Now this course outcomes are defined as per VTU syllabus. Now the first outcome that the VTU says is when a student completes this course, the student shall be able to what is the first CO? The student will be able to explain the concept of parallel computing, explain the concept of parallel computing and hardware technologies and hardware So, the first CO is explain the concept of parallel computing and hardware technologies. Now, the second one is obviously when you are learning about various computing techniques and hardware technologies, always there needs to be a compare and contrast. The second CO is going to be about compare and contrast. The what you are going to compare? You are going to compare and contrast the parallel architectures. That is what it is going to be learned in the second CO. The third one is illustrating the concept of parallel programming. So, the third CO is you are going to illustrate the concept of parallel programming. So, these are the three COs that are defined by VTU. The first one looks into the concepts of parallel computing and hardware techniques that are needed to be understood, and we are going to discuss in detail about some of the architectures and the hardwares. The second one is once when you learn n methods, n architectures, obviously it needs to be compared and contrasted so that we can choose or list out which one is best for a particular application. The third one is you are going to illustrate the concept of parallel programming here, because in your course the emphasis is paid on both hardware aspects as well as software aspects. Clear? So, that is why even the concept of parallel programming is also a part of your syllabus. Now, coming to the CO1 and 2, CO1 and 2 is going to be covered from module 1, 2, 3 and 4. So, as per your syllabus, module 1, 2, 3 and 4 is used for realizing CO1 and CO2, because in the module 1 you are going to study into the introduction, then you are going to look into the memory concepts. Here you are going to look into the various architectures, their applications, all four, because when I say a parallel computing, it is combination of both hardware as well as the memory concepts, right. Now, that is why you are going to look into module 1, 2, 3, 4, look into the various architectures from memory perspective as well as the processor perspective, and then you are going to compare those things. So, your module 1, 2, 3, 4 is used for realizing CO1 and CO2. Now, module 5 is for CO3. Now, this is how your syllabus is going to be spread across for attaining the CO1, CO2 and CO3. Clear? Module 1, 2, 3, 4 is for CO1 and CO2 realization, module 5 is for CO3 realization. And remember, we are going to study at an abstract level, not detailed design is going to be studied here. We are going to look into the concepts and the approaches that made them to evolve. And remember, the architectures has evolved over a period of time. It is not that they evolved simultaneous, it evolved over a period of time. Now, that is going to be looked into in this first module, and then the memory, processors, all are going to be studied in the 2, 3 and 4 module, and the fifth module you are going to look into the concept of parallel programming. Now, this is what your course promises you. At the end of a course, you will be able to learn these things. So, this is your course outcomes as per VTU syllabus, right. Now, once when you are clear with the course outcomes, what is the next thing that you need to know? Now, the next question that arises is, what should I do with this subject? That question arises, no? Now, the question is, where is this subject actually used? Now, I would say that course application, I am going to call it as a course application. Right. Now, where actually does this course is useful? Where actually does this course is useful? Now, if you want to learn about parallel computing, then if you want to learn about parallel computing, multiprocessor, multi-programming, etc., then probably this course is going to help them out. And again, if somebody wants to pursue their research in hardware, then probably this forms a base subject for them, because when I say you want a advanced computer architecture, obviously the research has to be there. The research is with respect to hardware technologies. Now, if you want to pursue a research in hardware technology, this course forms as a base subject, or else even if you want to do research in parallel computing, if you want to do research in parallel computing, these are the main 3 domains wherein you can use this concept of advanced computer architecture. The first one is, if you want to learn about parallel computing, this subject forms as a base. If you want to pursue a research in hardware design technology, etc., this forms as a first course to understand the hardware technologies. Or if you want to pursue a research in parallel computing, again this course forms as a first subject. Now, these are the course applications of this advanced computer architecture. I believe that you are clear with this now. The first one is you have learned about the objectives. The second one is the prerequisites, what is needed to understand the subject. The third one is course outcomes. Now, remember the course outcomes are as per the VTU defined one. 3 outcomes. The first one is they are going to learn into the concepts, then we are going to compare and contrast the various architectures, and the third CO is learn about parallel programming, right. And the last one is, you as a student, what is the use of this particular course. So, as I said, now this course can be used if you are learning parallel computing, and if you want to pursue research in hardware technologies, or if you want to pursue research in parallel computing, this course forms as a base subject. Clear with this? Now, with this introduction, now let me go to the module 1. Right, module 1. So, here in the module 1, you are going to learn about theories of parallelism. Module 1, again this is from your prescribed textbook by Kai Hong, right. Module 1, chapter 1, 2, 3. Module 1 is reference from textbook 1, chapter 1, chapter 2 and chapter 3. Reference for this is from the prescribed textbook, chapter 1, chapter 2 and chapter 3. So, in this chapter 1, we are going to look into the concept of theory of parallelism. Now, again when I say the theory of parallelism, nothing but what made them to get into this parallel architecture. Earlier it used to be a processor and it used to be sequential execution, because a program is nothing but a set of instructions and your computer can execute the instructions sequentially. It is not been made to execute concurrently, or it is not allowed to execute the instructions on a overlap fashion. It used to execute one instruction, it used to fetch the instruction, execute it, and then fetch the second one, etc., etc. It used to go like a sequential one. But because of the limitations of the sequential execution, they thought of executing it parallelly. So, that is where the concept of parallelism came into picture. If there are no dependencies, and if there are redundant resources available, obviously the concept of parallelism can be exploited. So, that is where the theory of parallelism started to emerge. I would simply say it is simply the issue of performance that pushed them to move from a sequential to parallel execution, because when you look into the performance, the main criteria that they look is the time needed for completion of execution. So, somewhere they want to reduce the time, minimize the total time needed for execution. Now, if that needs to be reduced, So, somewhere you need to do the job parallelly or concurrently. Now, that is where this concept of theory of parallelism came into picture, right. Now, in this chapter 1, as I said, no, theory of parallelism is from chapter 1. So, in this chapter 1, you are going to look into the state of computing. When I say the word state of computing, it is simply you are going to look into the history of computing. When I say the history of computing, I think somewhere you would have come across this history of computing in your first semester C course. No, there I think, do you remember somewhere your teacher would have told you 1G, first generation, second generation, third generation, fourth generation. Do you remember those things? The various generations in computing. Probably we will recall it again in this class. The first generation, second generation, third generation, fourth generation, etc., etc. Now, because they have looked into the way a concept has been evolved, and somewhere they have named it as a generation. Whenever you see a major shift from a approach, then they have made it as a generation, right. Now, I believe we are in the 5th generation of computing. Now, that is what you are going to study, the state of computing. The second one is you are going to look into multiprocessors and multicomputers. Multiprocessors and now, is there any difference between multiprocessor and multicomputers? Yes, the answer is yes. Here, in case of multiprocessors, many processors are working on one particular job. Even in a multi-computer also, many are going to be working on one, but the only difference that makes is somewhere the sharing of a resource. In case of a multi-computers, the resources are going to be exclusively allocated, but whereas in a multiprocessor, the resources like memory, etc., may be shared, or even it may be provided a redundant fashion. Clear? Right. Now, that is the thing. Now, in the third one that you are going to look is, you are going to look into multi-vectors and SIMD. SIMD computers. Now, what does this SIMD stands for? Single instruction, multiple data. Again, looking into the way the instructions are executed and the way the data has handled, they have classified into 4 categories. So, that classification we are going to study in detail in the coming classes. Single instruction, multiple data computers. This is a very widely used one. Earlier it used to be SISD. Now, it is MIMD, multiple instructions and multiple datas. Now, it is nothing but the way your instruction and data is handled gives them a classification, Flink's classification. There are 4 categories that we are going to study in detail in this one. The next one here you are going to look into PRAM and VLSI models. Right? You are going to look into PRAM models and VLSI models because the technology supported this integration. Nowadays, you have a very high density integration or fabrication. So, that made it possible for multi-processors to be accommodated on one single chip. Because of this VLSI technology, it allowed multiple processors to be etched on one single chip, right. And the last one is you are going to look into the track of how a architecture developed. Track of how the architecture, I do not say it has developed, evolved. So, these are the 5 things that you are going to study in chapter 1. The first one talks about the state of computing, and then the second one talks about multiprocessors and multi-computers. The third one, it talks about multi-vectors and SIMD computers, but when it comes to parallel computing, it is MIMD computers, then PRAM and VLSI models. The last one is you are going to look into the track of how the computer architecture evolved. the path of the computer architecture evolved is going to be looked into in detail in chapter 1. So, this is the outcome of chapter 1. Clear with this? Right. Now, let me go in detail into the first one. What is the first one? The state of computing, right. Before I look into the history of computing, can somebody say when does this concept of computing came into picture? When does this concept of computing came into picture? Is it some 10 years, 20 years, 30 years, 50 years or a few hundred years? No, I personally believe that the concept of computing came into picture whenever a human civilization started to evolve. Whenever there is more than one entity to be considered, now there the concept of computing came into existence. For example, if it is more than one, then obviously you need to know a little bit of mathematics for computing, for counting. Now, from counting a computing came into picture. But when you look into the early history, they all say that somewhere when you are a child, you would have come across this, no? Abacus. So, I think it was started somewhere around 500 BC in China. There was a abacus which started in 500 BC. Now, this is a recorded history of a early computing device, and this computing device is a mechanical in nature. Clear? I am repeating again, this computing device is used for calculating, and this calculating device was mechanical in nature. It used to have the beats, then the rows, etc. over there, and also since it was involved, many mechanical parts were involved. Integrating and then computing was sometimes error prone. It was not that much easy when you are using a differential engines for computing. Then came the concept of binary mechanical engines. Now, I believe this started in 1940s. Binary mechanical engines. I am using the word binary. Binary is 2, 0 and 1. So, the concept of using only two symbols in a computer, 0 and 1, somewhere started to get evolved in late 1940s, and from there on, instead of using n number of symbols, they have limited it to two symbols, zeros and ones. That is where the binary mechanical engine came into picture. Clear? And then afterwards again I think in 1944 IBM came up with a computing model that they used to call it as hardware mark. This was the very first electronic computing machine. This was the very first electronic computing machine which consists of zeros and ones, a binary computation, right. Now, if you look into this way back in 5000, now if you look into the difference of the years for this computing to get evolved, it took centuries. The earlier one, it was a mechanical device. From there it shifted to engines. From there it shifted to electromechanical, and from there, from electromechanical, it shifted completely to electronic component, and again they started to use the concept of zeros and ones. Look here, the concept of zeros and ones were introduced here even in a electromechanical components. Now, the same concept of zeros and ones were used completely. The mechanical components were replaced by electronic components, because during this period the concepts of vacuum tubes and everything were able to support electronic computing, because the technology needed for that started to evolve parallelly. It is because of the evolving of the vacuum tubes that led them to use this electronic computing machines. Clear? Now, this is how a computing started. A brief history from abacus to Chinese model to the present computing model. If I say what a computer is, you would simply say a computer is a electronic computing device. From here to here, the concept of that bare computing machine got evolved in 1944 with thanks to IBM. Now, this is how the concept of computing started to get evolved. Now, if you look into the generations, now just let me brief up the generations. As I said, no, generation 1, 2, 3, 4, and at present we are in generation 5. So, I am going to call it as first generation. Now, when did this first generation started? It started in 1945, and then it was there for till 1954. 1945 to 54. Now, when you look into this first generation, what was the technologies available? The technologies available were vacuum tubes. Vacuum tubes were available. What was the technology that was used? They used to use the relays for memory, right. So, these were the two major things that were being in the first generation, clear. And this first generation computing devices were able to perform fixed point arithmetics. So, they were able to perform fixed point arithmetics, right. A machine language. The language that was used was a machine language, or simply we would call it as a assembly language. So, it was either a machine language or a assembly language, and the software used was this. Now, the third question is, how many were able to use? It was only a single user and a single purpose. It was not able to perform multiple tasks at any given point of time. Only one user was able to handle it, and it was to perform one single operation. Again, your data needs to be loaded, all those things. So, all those things were evolved here, clear. And if you look into the examples of the first generation, now you would have you remember this ENIAC model, and then as I said, now the IBM 701 model. So, these were the computers in the first generation, clear. So, it started in 1945 and lasted till 54, because after 54 it was the evolving of transistors. The vacuum tubes were replaced by transistors. Because of this, there you see a second generation getting evolved, and vacuum tubes and relays were used for memory purpose. They were able to perform fixed point arithmetic, assembly language, and it was meant for a single use. And the models were ENIAC model or IBM 701 were some of the examples of the first generation computing, clear, right. Now, let us go to the second generation. Now, if you look into the second generation, when did the first generation end? It had ended in 1954. It starts in 1955 and then 1964, right. It started from 1955 and then ended with 1964. Now, what was the technology that was used here? In the first generation, it was vacuum tubes, but here they started to use transistors. The discrete transistors were available, right. And then again, core memory technology was available. Core memory technology was available. What was the capability offered by the second generation? So, they were able to perform floating point arithmetics. In the first generation, it was a fixed point arithmetics, but now they were able to perform a floating point arithmetics. And then what about the software that was used? So, somewhere the concept of high level language started to get evolved. People started to move from a assembly language to high level language in the second generation, and then again they introduced the concept of libraries or modular programming, or I would say reusability concepts were introduced. Reusability is nothing but when you write a code of a particular program, the same can be used. And then they had process monitoring, right. Now, they were able to look into the performance issues here, clear. Now, this is the second generation. If you ask me to list out some of the examples for the second generation, I would say IBM 7090, I think IBM 7090 model, the another one CDC 1640 or something, I do not know whether I am correct or not. 16 CDC 1604 is the model name. So, these are some of the examples of the second generation computer, CDC 1640, IBM 7090, or some of the models that were used in second generation. The duration of second generation again was 9 years. Now, after the second generation, they moved into the third generation. And again, if you look into the third generation, what is the change in the technology? The change in the technology is, instead of transistors, they were able to integrate multiple transistors onto one single chip. So, that is where the concepts of ICs started to get evolved. ICs, third generation, 1965 to 74, right. Again, each is of 9 years duration. Now, the technology was, from vacuum tubes they moved to discrete transistors, from discrete transistors they moved to integrated circuits, and then along with this they were able to perform multiple programming. They were able to perform multiple programming, and somewhere if they were able to perform multiple programming, then they started to use the concept of pipelining. Multiple programming and concept of pipelining. Look into the concept from where it evolved. It evolved somewhere in late 70s, multi-programming and pipelining concepts. So, you are going to streamline the resources allocation in such a way that the instructions can be executed concurrently, so that your total time needed for execution is going to be reduced. So, that is where the multi-programming and pipelining concepts came into picture. And again, for enhancing, they have the cache technology started to get evolved. The memory, allocating a memory exclusive to the processor, the cache concept started to get evolved. It is because of this you see a better increase in the performance, right. Now, when you look into the softwares that were there, instead of sequential programming, they were able to have multi-programming and they were able to perform multi-programming and time sharing. Multi-programming and time sharing. Once when you have the concept of multi-programming and time sharing, obviously you need somebody to maintain all this. So, that is where the concept of OS also started to get evolved. The concept of using a operating system also started to use. And now, coming to the number of users who can use simultaneously, it was more than one. So, multiple users and multiple applications were able to be run on this, right. Multiple users and multiple applications could be run simultaneously. If you want to give me the some of the examples of the third generation, I would say IBM 360. I think this probably was revolutionized the concept of computers. This IBM 360 made it possible for a computer to move from a research university etc. to a layman to on his desktop. Now, that is where this concept of IBM made it possible for a computer to be accessible by everyone, right. And then IBM 360, then PDP series, PDP 8, then 11 etc. all this series started to get evolved. I think in your computer architecture computer organization subject, you would have studied PDP 11 architecture, right. Now, that is nothing but a third generation computer, clear. So, like that the third generation started to get evolved. Now, after third generation, now we look into the next generation. The next one is the fourth generation. When did the fourth generation started? It started in 1975 in 1990, right? Now, if you look into the technology that supported this fourth generation, again it is VLSI. The technology was VLSI integration, huge fabrication or n number of discrete transistors were able to be integrated on one single chip that somewhere supported, and then the concept of semiconductor memories came into picture. The concept of semiconductor memory came into picture, then multiple computers were able to get integrated. Computers integrated. Now, that is where the concept of communication started to get evolved, so that multiple computers can be connected. Vector supercomputer started to get evolved, right? Now, this is with respect to the technology and everything. What it can do, as I said, no, it is able to run multiple applications and multiple users are supported, right? Now, if you look into the some of the examples for this, again IBM 3090 is the model that was there. Again CRAY series. So, these are some of the examples of computers that were there in the fourth generation. Clear? And when it comes to the programming language, now as I said, in the third generation itself, it started to evolve the high level languages. Here, along with the high level languages, so the compilers and interpreters were used. Compilers and interpreters. Now, what is the use of using these compilers and interpreters? Now, earlier it used to be machine dependent code, but now they started to move from machine dependent to machine independent programming, and that was possible by the changes or the support of the hardware, and then the compilers and interpreters made it possible for parallel processing. Compilers and interpreters for parallel processing. So, they made it possible for this. Now, if you look into, as I said, the examples are IBM 3090 and then your Cray series computers architectures. So, this used to represent the fourth generation. Now, coming to the fifth generation, so it started from 1991 onwards. So, this is the fifth generation computers. Now, what is the change in the technology that you see? As I said, now again you have got advanced VLSI capabilities are there, and then again you have got a concept of scalable architectures. Now, that is where the demand started to raise, because they wanted a computer which can scale up easily with reference to performance and the job it can take up. Now, that is where this scalable architectures came into picture, and then again super scalable processors. Scalable architectures and super scalable processors came into picture, and again somewhere concept of system on chip came into picture. The concept of system on chip came into picture. All the requirements are going to be fabricated in one single chip. It could be the processing power, the memory, IO interface, etc., needed for that particular application are going to be fabricated on one single chip. That is where the power requirement was able to be reduced and automatically the performance was going to be enhanced. So, they were generally for a specific application, right. Now, apart from the SOC, now till now it used to be homogeneous computation. From a homogeneous computation they moved to heterogeneous computation. Now, what is meant by heterogeneous computation? Till now the nature of the problem that used to be solved was a similar one, but here from homogeneous they started to move to heterogeneous processing capabilities. And if you want to name some of the earlier computers that were into this is this is where the Intel came into picture, Intel series. So, this is where if I want to name some of the earlier 5th generation computers, now I would say the Intel series came into picture, that they were the major players at that instant. Now, somewhere they were able to push back the IBM and they came into main picture, right. So, the Intel series, and again IBM was also there, I think IBM 9000 series something, but because of the technology that was adapted by Intel for fabrication of the processors made a huge impact on the way the design of the architectures came into picture, right. Now, we will study about this the approaches that have been used by Intel and what made them for everybody to follow it. So, this we are going to study in detail in when we take up the architectures, right. Now, this is how the generations are going to be looked into. Basically, every generation they are going to look into the first thing is the technology and the approach that is being used or the architecture that is being used. That is the first one. The first generation is started with the vacuum tubes, and by the fifth generation it was very high density VLSI fabrications were. Now, we talk about nanometers, right. And then looking into the computation, earlier it used to be single user, from single user now it is able to cater to heterogeneous users, and whatever the challenges that were being posed from moving from one generation to other, everything was addressed and they were able to evolve from a single to a heterogeneous compatible capable computing machines. Now, this is what we are going to look into the 5th generation computers. So, this is how your architectures are going to be looked into. Clear with this? Now, with this I am going to end my today's lecture.